Hello, everyone. Let's get started. Welcome to the MIT Mobility Forum, organized by the MIT Mobility Initiative. I'm Professor Jinhua Zhao, Professor of Cities and Transportation at MIT. Today, I'm really glad to have Professor Mircea Dinca join us, talk about his research on sustainable battery for mobile application. As many of you know, one major effort to decarbonize transportation is to develop the electric vehicle, of which the battery technology has a heavy reliance on cobalt, nickel, and lithium. And as you know, there's has a lot of consequences on the environment, on the social and political costs there. So there's been a lot of effort to replace or reduce the reliance on cobalt and nickel. But our alternative strategy is to completely move away from this inorganic oxide and to use redox active organic material. But the problem of those organic materials are typically have this high solubility, which hurt the cycle life of battery, and the low conductivity, right? So here, we invite Professor Dinca to present a new research that introduced a new organic molecule called TAQ, actually quite a bit solving both of these problems. So this is today's focus. And let me reinforce the norm of the forum before I properly introduce Professor Dinca. That is, I invite everyone to contribute one idea in the chat, either a form of a comment or question to Professor Dinca's presentation today. Also, to warm up the audience a little bit, I invite everybody in the chat to type in your organization, location, and times, so that will also give Professor Dinca a sense of who are the audience here. There's quite a bit diverse, I assume, but here, let me, myself, MIT, Cambridge, MA, 12. No, let's see, there are from Smart Transportation System, MIT, Chicago Transit Authority, Texas Transportation Institute, Ohio State University.
One chat box.
Colorado DOT, WABI, Amtrak, US DOT. Great, thank you. Yeah, please go ahead and type in your organization here. Professor Mircea Dinca, first of all, born in Romania, and now is a professor of energy at MIT. His research is on the storage and consumption of energy and its global environmental concerns. The focus is really the synthesis of novel organic and inorganic hybrid material and the manipulation of their electrochemical and physical properties with a current emphasis on this microporous material. The cornerstone of the research is really develop this inorganic organic synthesis, but as well as a rigorous physical characterization, which allows to delineate the important structure-function relationship that guide us in the design of a new material. Without further ado, let me pass the forum to Professor Dinca. Monsieur, please.
All right. Thanks, Jinhua, for the invitation. It's a very different audience for me, so thanks everyone for being here. It's great to see you're really not even from the US, but from all over the world. So this is great. So I thought that what I should do was actually, since I don't really know the audience. I'm a scientist. I'm a synthetic chemist at heart and by training. Although by virtue of being at MIT, I think I'm turning into a bit of an engineer. And we're working on a lot of different functional materials, making devices, and trying to address various energy issues. So for today, I thought I should actually start from a much more general premise, especially when it comes to transportation, and that is some statistics that I'm sure most, if not all of you, are aware of. Right? If we're driven by environmental concerns related to the footprint of transportation on greenhouse gas emissions, transport obviously makes a big part of that. And in particular, personal vehicles are maybe 2/3 of all of that transportation. So you might wonder, okay, well, fine. So let's start from a blank slate. How can we actually propel these cars? Okay, how do we get to batteries even, right? And are batteries the best option? And so this is a table that basically looks at energy density, if you will, how much juice it can put in your tank. And so the status quo right now is still petrol, diesel. You can see that in terms of kilowatt hours per kilogram or gravimetric or volumetric density, they're pretty high. Okay, and that's what makes them very attractive. You can put a lot of juice in a small box and your car can travel for a long range. So what's important to realize, though, and from a scientific perspective, is that none of these things are actually energy producers. They're just energy carriers. So fuels are just an energy carrier. They're not an energy source. Ultimately, the energy source, even for fossil fuels, is the sun. But we can then ask, okay, fine. So if you want to reduce CO2 emissions, what can you replace this energy carrier with? And you look at this table and you're like, oh, wow, hydrogen is 3 times as dense in terms of energy than petrol and diesel. And that's on a gravimetric basis. So you can pack a lot more juice in a kilogram of hydrogen than you can in a kilogram of gasoline. The problem with hydrogen, we'll talk a little bit about this and why, I'm sure, again, many of you are experts maybe in this, but one of the problems is volumetric density, okay? It's a lot lower than gasoline. But then you look all the way down and you realize that batteries look terrible compared to all of these chemical fuels, right? And that is a reality, okay? And I think what's interesting about this, and it'll become obvious in the context of my presentation today, is that obviously energy density is not an all be all. We all know that EVs are kind of winning out, especially when compared to hydrogen, and they're increasing their market share even relative to diesel and petrol. Okay, so what's wrong with hydrogen? Okay, it turns out that hydrogen, actually, a hydrogen car is much older than a gasoline car. And the very first automobile is actually an internal combustion engine made with hydrogen, in the early 1800s even. And that's before we even knew what petroleum was. We knew about hydrogen and we knew that it carried a lot of energy. And this has developed throughout the years, all the way to the early 2000s, I would say. But then it kind of stopped. And of course, there's still people who are pushing hydrogen, and I think for good reason. But EVs, right around 2000, 2010, EVs started sort of eating into this green revolution that was promised by hydrogen. And one of the really big issues, and one of the things you can do is early on is look at buses, and there have been a lot of all over the world projects to replace bus fleets in cities with hydrogen buses, and all of them, almost without exception, were ill-fated. They basically failed for many reasons. They were much more complicated to repair. They didn't quite have access to hydrogen, which really highlights some of these issues, logistical issues really, that have to do with hydrogen. So what are the issues? Hydrogen production is one. This is mostly or almost only an environmental problem, because most of the hydrogen that we make today is actually derived from fossil fuels. So this really doesn't solve the CO2 problem. In some sense it does, because when you make hydrogen on a site, you can capture that CO2. The fact that it isn't captured, that's a different problem, but it is a much more concentrated source of CO2. So you could, in fact, capture that. And of course, if you burn it in a car, that's much more dilute and distributed. But making abstraction of this, we could, in principle, make sufficient hydrogen, even from hydrocarbons, to power fleets of cars on hydrogen. But distribution is a different issue. Okay, so when it comes to the infrastructure that would be required to make hydrogen and distribute hydrogen, that becomes a real issue. And this is one of the main reasons a lot of these projects on hydrogen cars and buses didn't really take off, or were just not sustainable. And so that's something that, in principle could be solved with smart people and systems and such, but that is currently a big issue. And then finally, you have this issue of storage of hydrogen. And if you think about how much juice you can get in a kilogram of hydrogen, that's really nice. But how much juice you can get in a liter of hydrogen, that's a very different story. And so there are lots of researchers today even, but much more so in the early 2000s, because it was prompted by a DOE a push on hydrogen. How do you store the hydrogen? And if you're looking at even compressed hydrogen at 200 bar, for your car to run about 300 miles, you need 4 kilograms of hydrogen, and that takes 110 liters. That is much, much bigger than your typical gasoline tank. So it basically makes your car, if you keep the car the same size, much less functional. You have to get rid of your luggage or your kids or one of those, because you just can't carry all that volume in your car. And there are better ways or more efficient ways to pack hydrogen, but they come with added complications, complexities to the system, which adds cost. So for instance, doing liquid hydrogen, that reduces the volume by about a half to only 57 liters. That now is about the same as a gasoline tank, at about 15 gallons or so. But it's much more complex. It's not just the volume of the tank. You need to cool it. You need liquid nitrogen. You need liquid helium, actually. And so there are other chemical means to do this, but none of them have actually hit the so-called DOE targets that the DOE had set early in the early 2000s on these things. So basically, when it comes to hydrogen, you have all these things that are working against you. You have the distribution issue, you have the production issue, and you have the storage issue. And the storage doesn't have to do just with the car itself. Even when you produce the hydrogen on site, as might be available through this scheme that is completely green hydrogen through biological photoelectrochemical splitting or sunlight or whatever, you still need to keep the hydrogen on site. And keeping tanks of hydrogen, one, is somewhat costly, but two, it actually bumps into a user perception problem, because people just don't want to have big tanks of pressurized hydrogen around them or in their cars. Every time you talk to people about high pressure hydrogen, they think about the Hindenburg disaster and people jumping off of, flame engulfed Zeppelins. So, if you ask me, I think that there's very good promise in hydrogen, but there's a lot of logistical and not so many technical, other than the storage part, not so many technical issues as there are sort of like consumer satisfaction and logistical issues that would have to be overcome. So another means to deliver the hydrogen that people have imagined, of course, is through the grid. You just use the electricity to split the water, and you can do this at home if you have an electrolyzer that's small, or you can do this at a filling station. So imagine your gasoline station just having an electrolyzer and delivering H2 on site. But then you actually start thinking about, okay, well, so basically we're using the grid to make hydrogen. And what is the efficiency of that process? And we'll talk about that. But you're basically using electricity to convert one form of energy, and that is electrical energy, into a different form of energy, which is chemical energy. And then you're burning that hydrogen either in a fuel cell or in an internal combustion engine, which are governed by their own efficiency maxima. So you have to convert all of these energy conversion steps, each of which are not 100%. And so we'll discuss a little bit more about that. But when you then go back to the grid and say, okay, well, let's overload the grid with all the electricity that we need to power all of our cars, then it makes a lot of sense to just use the electricity as is. So then you go back, this is more or less showing the same sort of data as in that previous table, but looking at two different measures. Now you're looking at specific energy on the x-axis, so that's how much juice you can put in your energy storage device, and specific power on the y-axis. This is different. This is not just gravimetric versus volumetric. This is now juice versus how fast you can use that juice, or how fast you can recharge your battery or your tank or what have you. And so you want to be essentially on the upper right corner. And that's why combustion engines on diesel work so well, because you have a lot of juice that can be burned or refilled really quickly. And so getting to this upper quadrant, right quadrant, is really difficult with basically anything else other than liquid fuels. So on the right-hand side, on the lower quadrant, you have batteries. We'll talk a little bit more about these. So they have a lot of juice, not quite as much as the liquid fuels, but they don't actually work that fast. So if you want to move your car really fast, that actually discharges your battery, as we all know, much faster than if you drive your car slowly. And that's just a fact of how the batteries work. It's actually all chemistry's fault. The chemistry inherently involved with the battery is slow. It just has a slow rate, and there's not much we can do about that. But on the upper left quadrant, you have so-called capacitors. Now, these are actually terrible at storing energy, but they can deliver it really fast. And that's because they are not actually chemistry driven. They're all physical processes. You just adsorb ions onto a surface and you desorb them. And that can be a really, really fast process. So they each have their uses. You're going to be using capacitors when you want to accelerate really fast, like starting from 0 to 60, you might want to use a big capacitor. But then as you reach 60 miles an hour or whatever your steady speed is, you're going to be using the battery because that's much slower and you don't need to have these huge power inputs. So both are very useful. And this is kind of where our story starts with batteries, basically saying, okay, I worked on hydrogen, and I think it's a fascinating problem that and eventually I hope we can go to hydrogen, because it is potentially an extremely green, extremely renewable resource that literally only uses sunlight and water. But it has a lot of issues related to efficiency. So basically, the energy this is the lower part of this graph here, the energy that you use, you have to then transform it into chemical energy by electrolysis. That saps your energy efficiency. You then have to somehow put your hydrogen in the car. You have to compress it, you have to liquefy it, you have to make the system, and the cost associated with making that system that contains your hydrogen, that's another efficiency loss in a well-to-wheel sort of efficiency calculation. Then you have to transport the hydrogen, use the filling stations, all of those have losses. And so that's another efficiency sap. And then you finally have to transform the hydrogen into some mechanical work. And usually that's done with a fuel cell, and that's another efficiency sap, right? So the overall efficiency, the rate from the point in which you take the energy, let's call it solar energy, and you deliver it to a car to propel it forward, it's only about 25 to 35%. Whereas if you use an electric vehicle or an electric battery, you don't have to do all these energy transformations. So you're looking at 70 to even 90% overall efficiency rate. And so, you can think of it however you want in terms of energy, in terms of joules, right? Energy quantity or dollars. That's, you get 3 times the bang for your buck if you do EVs. So capacitors are, as I mentioned, some of the simplest devices, and I apologize if you are familiar with all these, but I just wanted to show you a very simple concept of how a capacitor works, right? So these are very used in all of the EVs. They are these devices that deliver a lot of power, but they can't hold a lot of juice. And so they do so because they're basically, it's very simple devices. You all know a capacitor has 2 plates, and you have an electrolyte, and at rest, when there's no potential applied to those 2 plates, the ions move sort of randomly in that solution. Then as I bias my capacitor to charge it, let's say, so I create a standing electric field that, let's say I bias my electrode negatively, then the positive ions are going to move towards the electrode that is negatively charged. And then the negative ions are going to be like, well, we kind of want to hang out with the positive ions, so we're going to go on top of them. And so that basically creates a capacitor. And the capacitance of a capacitor increases with the area of the plate. So if you have a really high surface area material that is conductive enough to be charged, you have a so-called supercapacitor. And again, these are very common devices. They're used everywhere. The problem with supercapacitors is that it's really hard to find a material or to make a material that is both high surface area, such that you have this high area of the plate, and conductive. And basically, all commercial supercapacitors are made from carbon, various kinds of carbons, activated carbons. You can think of these as just these black powders that you can make from burning coconut shells and olive pits and eggs and whatever. Basically, you can carbonize anything that's organic and make it into a carbon. So one of the things that my lab did a number of years ago now, 7, 8 years ago, is to show that we can make materials that are not carbon into a supercapacitor. And this was very exciting because at the time, or even today, this is pretty much the only material that's not carbon that can actually make a capacitor that's both porous and conductive. And so it became pretty evident at the time that there was something special about these. And the graph shows basically how much capacitance. You can think of this for a capacitor in terms of juice, again, like how much juice can you put in a capacitor as a function of the surface area that the plate has for the capacitor. And for some reasons that, quite honestly, we still don't quite understand, we could do a lot more with our materials than with other materials. And so the only problem was that we basically had made a very expensive, very high performance supercapacitor, but very expensive because carbon is really cheap. So if you want to compete on a practical basis with carbon, you basically, well, it's really hard because anything else that's more expensive than carbon, any other element that's more expensive than carbon, which is pretty much everything, is going to increase the cost. But we did pair up with a car company that, in principle, doesn't really care about cost. And so, so we've been working for 7 or 8 years now with Lamborghini to basically make an electric Lamborghini. And, you know, this is exciting, but to me, it actually had a lot of attraction because it's a really interesting idea that they were after. They wanted to say, you know, they came to me and said, you know, if we have capacitors on one side and batteries on the other side, capacitors have high power but low density, and batteries have high density but low power. Can we combine them somehow to make the best of both worlds? So basically make a capacitor that has a lot more juice but continues to have high power, or a battery that has maybe a little less juice but works at much higher power, as you might need for a muscle car. And that to me was challenging and therefore exciting. How do you think about making material that actually does that? And then the other thing that was interesting in working with them is that, you know, I think of a Lamborghini as kind of like a way to introduce sort of the latest and the greatest that eventually might make it into mass production cars, right? Nobody's going to make money or fame really by having something in a Lamborghini. They sell about 10,000 cars a year, so not a huge volume. But if you demonstrate something in a high performance car that can then be sort of optimized for mass market production in a VW or a Toyota or something, then that's much more impactful in my mind. So in any case, we paired up with them, and then eventually we came to the conclusion that our material, while performing well, is actually too expensive, even for a Lamborghini. So back to square one, we said, okay, what is happening? You know, what makes a battery expensive? Okay, so again, just kind of like trying to be naive about it and thinking from square one, what is a battery? What makes it expensive? And so again, apologies for those of you who are well, who understand these well, but battery is itself a fairly simple device. You have an anode or the negative material, and then you have a cathode or the positive material. Ions get exchanged. Ions meaning lithium, could be sodium, could be potassium, but in general, it's lithium right now. So you have typically a liquid electrolyte, but could be solid. But in any case, that electrolyte establishes an ionic conduit for the ions, but the electrical circuit is established outside the battery and it powers your electrical engine and so on. So evidently you need three things. You need an anode material. This is typically graphite. There are companies out there that are looking at silicon, but there's not much else in terms of real with practical value for EVs. You have the electrolyte. Again, the vast majority, and I think all commercial batteries right now have a liquid electrolyte, but there are innovations out there in looking at solid state. Not going to talk about that today. And then the cathodes. We're going to focus on these cathodes because these are the ones, as I'll show you, that really dictate a lot about the battery, from cost to performance. And there's very little innovation on a compositional basis, basically new materials for cathodes. Okay, so here it is. If you break it down, depending on the market and depending on which battery technology you actually use, cathode makes up the largest cost component of your battery. It could be 50%, but it really fluctuates depending on variables between 30 and up to 70%. So it's by far, regardless how you look at it, the largest cost component of your EV battery. Then, of course, there's like manufacturing, depreciation, anodes, separators, electrolytes, all the current collectors, copper, aluminum, all those things. So what are the current traditional materials that are used in all of the EVs right now? It's basically, as Jinhua mentioned briefly, metal oxides. Okay, so N stands for nickel, M is manganese, C is cobalt. Nickel, cobalt, and manganese are sort of like the quintessential three elements, three raw materials that you need to make a high-performance battery right now. We'll see what the problem is with those, but it basically has to do with, so these are great. Specific energy tells you how much juice you can put in that battery. And you can see that these nickel cobalt batteries in various iterations are much, much better than anything that doesn't have cobalt or nickel. So LFP, we'll talk a little bit about that. LFP is actually kind of winning out right now because it's iron and phosphate, so it's much more sustainable. Iron and phosphate are not as critical as cobalt and nickel. They're not as rare as cobalt and nickel. And they're winning out again, despite the fact that they're really crappy compared to NMC. If you look at the energy density, again, how much juice you can put in it, it's less than half of an NMC battery. So all of the cheaper EV batteries or EVs in general will have LFP because it's cheaper, but they're not going to have huge range. And so again, this energy density is linearly proportional with range. You can't have juice, you can't have range. Whereas the higher end models, luxury EVs or, higher end Teslas, they will have these nickel cobalt batteries that will go for 50, 60, or 500, 600 miles. Okay. In addition to just how much range you get, the cathode dictates the power of a battery. So how well and how fast they can intercalate the lithium ions, they will often dictate how fast you can charge and discharge the battery. Not only how fast or how long do you have to wait at a charging station, but how fast can your car go, really, and for how long. So this slow charging of the cathodes translate directly to long wait times at the pump or the electrical pump, if you will. And even within these, there's basically just a phase diagram of all nickel, manganese, cobalt compositions, sort of on a triangle, but there's very little innovation outside of these traditional oxides. So what are the problems with these batteries? Well, let's take cobalt. Cobalt is really the biggest problem in any of these high-performance batteries. It starts from basically where it's found. 73% of the current production worldwide cobalt is in the Democratic Republic of the Congo, which we all know is only in name democratic. But that's where the cobalt is. And in addition to it basically being almost a single source worldwide in a highly problematic region, there's a societal cost that is really unacceptable, at least from my point of view. And that is that it's very well known that basically there's huge human right violations when it comes to where the cobalt is sourced. And unfortunately, I have to say that, even phones like mine right now probably has cobalt mined by some kid in the Congo. If you look at lithium and nickel, again, you actually see very centralized production of both of these metals. They're much, much cheaper than cobalt. Cobalt is by far the most expensive component in any battery because it's mostly refined as a sort of a byproduct of nickel, actually. But again, you see Indonesia, for instance, and the Philippines basically producing more than half of the nickel supply. And even though people think of nickel as like, oh, okay, if you look at the periodic table, people say, okay, the first row in the transition series is sort of cheaper metals, they're abundant. By some estimates, just in the last about 120 years, we have mined and used about 80% of all known nickel reserves on the planet. So by no means are any of these abundant metals really all that abundant. And then finally, you can look at phosphate itself. Okay, so LFP is touted, this lithium iron phosphate doesn't have nickel, doesn't have cobalt. So they're touted as the sort of up and coming replacements for NMC, for nickel cobalt batteries. But phosphate itself, depending on who you talk to, has huge societal implications. First, Morocco actually has 70% of the known reserves of all phosphate on the planet. So Morocco is a friendly country for now, but again, you have basically concentrated phosphate reserves in the hands of a single nation, more or less. It gets very complicated. The type of phosphate that you need for batteries is very, very special, very difficult to refine. Canada actually has quite a bit of that phosphate. But it also turns out that phosphate is, in fact, despite the fact that it's relatively abundant, is a critical resource for humanity in general. And it is an endangered resource because basically all of the phosphate that we mine today goes into agriculture. Phosphate is a critical added material, basically it's needed in agriculture. And so crops would die or it would not be as productive without phosphate. So it's estimated that if we start increasing the proportion of LFP batteries in EVs by about 2030 or 2035, we'll be using 5% of the world production of phosphorus for electric vehicles rather than agriculture. So imagine what happens if we then have to reduce the agricultural production by 5%. Okay. Okay, so all of these have their own issues. Okay, and there's huge biases and there's huge interests at play. Whenever you read a paper, you have to be, much like with the tobacco industry, you have to be careful where that information comes from. Who's telling you what and what are their ulterior motives about phosphate, nickel, cobalt, and so on. So this brings me to what I think is a much more sustainable alternative, but I'm happy to discuss with you even that, which is this organic battery. So basically organics, as I'm sure many of you know, organics are carbon, nitrogen, oxygen molecules. I think provably sustainable in the sense that there is a lot of carbon, nitrogen, and oxygen on the planet. From a market perspective, in the end, like whatever you do, if you want to have an impact in a capitalistic society, you would have to look at cost. And no matter how much, say, LCO or cobalt or nickel-based batteries, which are these colored graphs, fluctuate with the cost of the raw materials. The cost of organic molecules fluctuates, of course. They're also subject to the market forces, but they're generally in a much narrower range below the overall cost of all of those other metal materials. And that's because they are all derived from petroleum. So usually the question I get now is, well, wait a minute, isn't petroleum bad? Why are we trying to make batteries out of petroleum? And the answer is that petroleum is bad only when you burn it. We want to stop burning petroleum. We need to start thinking of it as an amazing resource that should be valued, not burned. It's kind of like, we could be using wood for heating ourselves, or we could be building houses with wood that will last for, hundreds of years. Then there is the environmental component of using organics. If you look at the whole production process of traditional batteries on these metal oxides, mining is extremely energy intensive and, of course, environmentally damaging. Processing the mined material is extremely energy intensive itself. And then further processing and making the batteries is also energy intensive, such that if you make a battery, say a typical nickel cobalt battery, you emit about 200 kilograms of CO2 per kilogram of battery. If you work with even the fanciest of organic molecules, that is reduced to about 5. So a factor of 4, if not more. Okay, so to the extent that you're driven by environmental standards, that I think is a powerful message there. What is the problem with batteries? Well, they cycle poorly. We'll get a little bit into this, but basically, when you make an organic battery, you want to be able to cycle, or you want to make any battery, you want to be able to cycle it at least maybe 2,500 times, if not 5,000 times. Think of it, if you charge your car once a day, that 5,000 is about 12, 15 years, right? So that is a regular lifetime of a car. For a phone, it's only about 2,000 cycles, because after about 3 years, people change their phones anyways, or at most 3 years. But with organics, you don't get nearly as many cycles, because organics eventually cross over from the positive electrode to the negative electrode. So basically, the battery looks symmetric now, and it just doesn't work. It has a 0 voltage. Or it shorts, which is a more problematic death. They're also not conductive. So a lot of these molecules are not conductive themselves, which means that even though they look good on paper, they should be able to take a lot of juice. They really don't, because by the time that you make a battery, you end up having to use a lot of additives. So long story short, I know I'm going a little bit over time. We made a molecule very cheap. It can be made from 2 commodity chemicals that are already made on the million-ton scale. And at any rate, meaning doesn't matter how fast we charge it or discharge it, the graph on the right shows you that it works better than even the best high-performance batteries made from nickel and cobalt, which is very exciting. On a gravimetric basis, on a volumetric basis, it works at least as well as the LFP, so it definitely beats out LFP. And then finally, so we basically got rid of cobalt and nickel, and now lately we've been able to get rid of lithium as well. And the lithium is problematic itself, because we all know it comes from very concentrated sources in a few countries only, and the cost can fluctuate by a lot. So we've replaced the lithium with sodium, and again, the performance almost doesn't take any hits. There's lots of other variables that people care about: safety, cycle life, being able to use different electrolytes. But basically, we can now make batteries that are, I think, performant and competitive on a practical basis with traditional oxides from just essentially oil. Realize it would take that long. I'm happy to leave some time for questions.
Great, thank you so much, Mircea, Dinca, on this. Maybe I'll start with some question and then invite the audience to type your question into the chat, right? So maybe I'll start with the TAQ. So tell us more about the the discovery or design process? How do you identify this material? What inspired you to find using TAQ as this organic anode on this? And also the second question is, given this is such a powerful new material, now you start from the kind of scientific research. How long would it take before they get to the actual pilot and the industrialized usage and commercial usage, etc.? How far away from that?
Okay, let me start with your first question. So basically, this molecule, I think it's a really cool story of scientific discovery, that came a little bit by serendipity, as many good things do. As I mentioned, we were working with Lamborghini, and it gets a little bit into the weeds of the chemistry, but we were looking at these NH2 groups because they had good properties with respect to increasing the conductivity. I mentioned that was really important. Yeah. And then almost by mistake, my two students here, Tianyang and Harish, discovered that what we were trying to make didn't really work out. Instead, they were kept crashing out, basically producing large quantities of this black precipitate that many students would have thrown away, because when you're a synthetic chemist and you make a black precipitate solid that you can't characterize easily, they just sort of don't even tell the PI, so they just throw it away, and they're like, okay, we'll just start over. But they had the insight to actually think about it. It's like, hey, wait a minute, like this is black, it could be conductive. And so they made a battery out of it before really knowing what it was. And it worked really well. And then they backtrack and they're like, what is this thing? Why is it working so well? Wow. So that's the discovery. And then, to answer your more practical question, so we do have a startup now, like I mentioned, it's called Dacus Energy.
We mistakes currently here. Often the amazing thing could happen out of this. Yeah. Okay, thank you. So the second question is on.
Yeah, this is not just in the movies. This happens in reality.
Right. Yeah. So the second thing on the hydrogen, right? You mentioned several things. Hydrogen, you feel like it's not really a technical question. It's somehow more of this logistical consumer preference. Many of these issues there. So you mentioned the quantum innovation even earlier than many of the ICE cars, electric cars, but then somehow stopped at the 2010, right? So here, do you think in terms of the overall societal pathway on hydrogen, we didn't design the whole process well? Or what can we do to actually revitalize this discussion on hydrogen and make it a potential meaningful pathway forward?
I mean, honestly, I think distribution is a huge problem. Where do you get your hydrogen? Let's say you buy a hydrogen car, and right now, honestly, Toyota is still leading the way, and Nissan and others, had hydrogen cars and fuel cells. Fuel cells are working fine. We can more or less put hydrogen, store the hydrogen. Okay, it's somewhat bulky, but it takes half of your tank of your storage space in a car, so it's not ideal. But the car is there. The cars exist, right? And they work well. Problem is, people can't get to the hydrogen. It's not easy to get to a hydrogen refueling station. And it's not even the production. I mean, yes, technically it's kind of like blue hydrogen, because it's still made from hydrocarbons. But in a way that produces much less carbon dioxide, right? And in principle, it could be completely green, literally just splitting water from solar. I think the distribution is a huge problem. Are there people who work on distributed hydrogen? So basically home scale electrolyzers, right? But even that requires you to buy an electrolyzer, and that requires maintenance. Right? It's not as easy as just having an electric plug that you can just plug in your car, right? So I think that is both a technical and a logistical problem. I mean, that's really it, really.
Right. So maybe last question from me, and I give it to John. At the very beginning, you start with this really back to the science fundamental here. If it's a side of the blank state, look at all the possibilities, right? From hydrogen, gas, diesel, battery, all the capacity of the things, right? So now you look at the whole thing. Do you think strategically, maybe particularly from scientific community, right? Are we covering most of the interesting ground here, or there's some major area that has a potential, but nobody's exploring, right?
There's lots of smart people out there that are working on all of those potential fuels: ammonia, methanol, fuel cells, ammonia as a carrier for hydrogen, all sorts of other things. I mean, you could have an entire course and still wouldn't go through all of them. So I think we are covering everything out there, right? I think there's a lot of really cool innovations in engineering, right? Like you can couple electric with solar, right? And there are people who make solar cars, or to the extent that that adds anything to the picture. Yes, we are covering from a scientific basis. I think we're covering all of those. In the end, it's still, what makes it to the market is still obviously dictated by cost and efficiency. And that's why I think EVs are the way to go right now. But I am hopeful about hydrogen myself, right? I mean, it would be an amazing fuel.
Great, thank you. Yeah, John?
Thank you so much, Professor. I mean, you really covered sort of very comprehensively, starting with this concept of energy source versus energy carrier. That elicited some commentary. The comparison of shifting from hydrogen to electric. So we had a very broad range of questions. Let me just maybe start out with a big picture question about innovation and how you think, what is the role of government in investing in sort of not just incentivizing this type of real core technology innovation like you and your students have worked on in your lab, but ultimately commercializing and bringing to market that innovation. And please feel free to reflect on any of the, your learnings from working with Lamborghini. As you mentioned, of course, it's a very niche car company, but do you have thoughts about, are we putting our chips in the right place from an investment perspective to actually bring this technology to market and really have an impact in what we're all trying to do, which is to reduce CO2 emissions?
That's a great question, and I'm not the expert on this. There are many people who understand policy a lot better, but I think maybe precisely why, from my standpoint of a informed observer, let's call it, I think we are doing some things from the government. Well, maybe less so in the next 4 years, but some things are done. Obviously, there's investment in, manufacturing on US soil for all these. I think that's good from a competitive standpoint. We want to be able to be independent of other nations with respect to, these critical technologies. But not enough. I think the single most important thing for not just vehicle technologies, but for the environment in general is obviously pricing carbon. That would have such huge repercussions on anything, right? From the cost, like it would basically push people to use more sustainable materials in batteries, for instance, right? If you look, because then instead of looking at just the fluctuation of the market, which is just dollars, you would be looking at the fluctuations in CO2 footprint. And then you would automatically migrate towards those that have 1/4 of the CO2 footprint than a cobalt oxide, right? And that to me, that would have such huge implications, not just on competitiveness of materials and environmental stewardship, but societally, right? Like if you just cut the cobalt production from the Congo, that would be good, right? So I think we're not that close to doing such a drastic thing as pricing carbon, but I think policy has absolutely humongous effects on technology and, embracing technology. I wish we had more time, but I have another startup company on ACs, air conditioning is an incredibly inefficient and a terrible technology that is absolutely critical. And there is just nothing out there. The market is so old and so entrenched that there's actually almost no incentive to innovate. And so they're using and making and selling these incredibly inefficient air conditioners. All of us are using them. They're terrible. There is technology out there that could make them 2 or 3 times more efficient, but none of the major producers are making and selling that technology because there's no incentive. And so that's a single instance where policy can have a huge effect on the environment on an increasingly important problem. So, and that's just something I'm aware of because I'm biased, but I think policy is, I'm sorry to say it, probably more important than technology in many ways.
Yeah. Okay, that was a big question. Let me try to hit some of the smaller, more specific questions from the audience. So Kim Saylor asked, would carrying the liquid hydrogen tank be as heavy as an EV car? Meaning, batteries, of course, add a lot of weight versus gas cars. There's commentary about it's not necessarily the hydrogen itself, it's all the equipment that has to go around the hydrogen to cool it or compress it. Any sort of back of envelope thoughts on the weight?
Yeah, that's an interesting. I never actually did that direct comparison, but my guess, my hunch would be that it is probably about the same, maybe a little lighter if you're looking at hydrogen, but vastly more problematic in terms of engineering, because you would have to put, if you're keeping liquid hydrogen, it would have to be in a cylinder. Because of how engineering works. And so, whereas a battery, you can put it anywhere, right? Like you can form it, you can shape it however you want, more or less. And so with a big cylinder, there's less maneuvering that you can do, right? In terms of how you design your car. It's also something that I think losses for liquid hydrogen is significant. So if you leave your car out in the Boston sun for, a month while you're on wherever on vacation, you might not have any hydrogen left by the time you're back. Whereas batteries are not quite as bad, right?
Just a quick follow-up on hydrogen. Terry Lewis asked, is there a market where hydrogen is feasible, perhaps marine?
Yeah, so that honestly, I don't know as much about. There probably are markets that are better suited for that.
Okay, Don McKenzie asked, how do organic and inorganic redox materials compare in terms of the kilowatt hours of battery capacity or kilowatt hours of lifetime use, rather than per kilogram of material, meaning the life cycle greenhouse gases like you presented?
Yeah, so that you can distribute, if they have the same lifetime, let's say 5,000 cycles, you can just distribute that CO2 and organics still come out on top. Generally, it really depends on the material. But for instance, these materials that I showed have at least as long life cycle, and that's just something I didn't show much, but at least as long life cycle as the inorganic ones. So they'll be much better in terms of CO2 footprint.
Fabulous.
It's 1 o'clock. John, do you want one more simple one, or?
There was one more just about, do you have any quick thoughts on lithium capacitors? This was from Soren Streep.
I don't know what, I mean, a lot of capacitors do use lithium. I don't know, commercial ones that do necessarily. Yeah, I'm not sure I can answer that.